Well, welcome everybody. Welcome to the inaugural lecture to be held by Frits Møller. I don't know if you noticed, but it's Julefrokost Friday, and there's a big bus outside, and I thought everyone was coming here, in fact, to kind of start the Julefrokost Friday, but obviously not. But you're, in fact, in the advantaged position that you both get an inspirational lecture here, and afterwards you'll get some drinks. So, I mean, it's a perfect mix for today. So I'm really happy that so many of you showed up here on this special Friday, and special because it's the inaugural lecture by Frits. And it has to start a little formal. I have to start a little formal. I have to introduce Frits, and he is tackling a complex area which I'm not necessarily the biggest expert in. So I got a little text, and I have to read it up to you, but it's meant as an introduction. The planning of the future energy system requires evaluation of future energy demand. And applying econometrics to analyze the past developments that may and can reveal patterns that may be used to model and forecast energy demand. Among other research activities, Frits has been involved in the development of the EMMA model. And if you notice, probably he'll talk about some of those models along the road. They all have fancy Frida, Emma names like that. I don't know whether it came by coincidence or was there any plan behind that, but it's at least it makes me stick in my head at least, so I know the Emma model. So those models used for official projections and analysis of energy demands by the Danish Energy Agency and Energinet.dk. Frits has also analyzed electricity demand with an hourly resolution and develop methods to forecast the profile of hourly electricity consumption both at a national level and in local areas. Another application of econometrics has been analysis of waste generation and the development of the, another name, Frida model used by the Danish Environmental Agency. So that's kind of a little bit on the scope of what Frits is working on, and also something he will talk about today, I believe. Who is Fritz Mohonasen? He holds a master in economics from Aarhus University from 1980. He has been employed as a scientist and a senior scientist at the Energy Systems Analysis Group at Risø National Laboratory from 1980 to 1992. Then worked as a senior scientist at the Department of Policy Analysis at the National Environmental Research Institute from 92 to 97, and then acted as head of research program Energy Systems Analysis, now at DTU Management Engineering from 1997 to this year, and is now, after today, in fact, or, well, I mean, I've been for a while, but after today, right now publicly, going to be a professor in applied econometrics and energy demand modeling. We are looking very much forward to your lecture today. And the scene is yours.
Thank you for a very nice presentation. And yes, I'll give a lecture on applied econometrics and energy demand modeling, or in short, applied modeling. Now, to some of you, econometrics may sound a bit complicated, but in practice, it is just a method for analyzing a set of data and hopefully extract some both relevant and interesting information. And as I'm used to say, it helps to know what you are looking for. Quite often the data doesn't give you a very clear answer, and it may even happen that it gives you a somewhat surprising answer, and that's when it actually becomes interesting. If it's not an error, you might actually learn something new on that account. So I've been so fortunate to be one of the first to analyze a number of different data sets. When I started at Risø for quite many years ago, the first data set I looked into was the energy balances from Statistics Denmark. And in this, I looked for structural changes, trends in the energy consumption and effects of prices. And I actually developed a little model called Indus that for quite many years was used to forecast industrial energy consumption in Denmark. Later, the model was revised and extended to cover all different kinds of energy demand in Denmark, and it became the Emma model that I shall talk a little about later. Another set of data I've looked into is the ESOC data on the generation and handling of waste. This data is collected by the Danish EPA, and again I looked at structure and changes and trends in the waste generation, and I developed a model called FRIDA that is used for in the waste planning by the Danish EPA. Also developed a small EU waste model, mainly looking at municipal solid waste in different EU countries. And this model is used by the European Topic Center on Waste. Now lately, I've got access to statistics from all the metering of electricity consumption by individual customers. These data are collected by Energinet DK and the Danish Energy Association. And in this data, I analyze hourly consumption profiles, and I've developed two small models. One looking at the profile for the national hourly electricity consumption, and another looking at local, the profiles in local areas. And I'll come back to those in a little while. So I'll start with saying little about EMA, and then I'll go on talking about hourly electricity consumption. Now EMA, it stands for Energy and Environmental Models for ADAM. The data, as I said, is based on the energy balances and the national account statistic input-output tables from Statistics Denmark. It's an econometric model estimated on data from 1975 to 2010, and it converts forecasts of the economic development into forecasts of the energy demand. And it's linked to ADAM. ADAM is a model used for official forecast of the economic development in Denmark. And EMA may run either as an integrated part of ADAM or as a satellite to ADAM, where we take the economic forecast from ADAM as given. In most analysis uses, we use EMA as a satellite to ADAM. It has been used for official forecast analysis by the Danish Energy Agency and by Energinet DK for the last 15 years. And the model is what we call an open source model. That is the model, the data, simulation software, and some of the analysis, a few of them, may be downloaded from the homepage of the Danish Energy Agency. Now, quite many people have been involved in the development of EMA, and some of you are here today. I shan't mention you all. Just say that at the moment, at present, the model is maintained, further developed in collaboration between the Danish Energy Agency, Energinet DK, DTU, and Thomas Thomsen. Now, at the overall level, EMA describes aggregated links between the economy, energy demand, and energy-related emissions. So at the top, we have the EMA model giving the economic development. In EMA, we distinguish energy consumption between production sectors, households, and from transport. And in the first step for production sectors and households, we determine the electricity demand and the demand for other fuels. Then in the second step, other fuels are divided into solid, oil, gas, district heating, and biofuels. For transport, we distinguish between transports of goods and transports of persons. And finally, the model calculates emissions of CO2. Looking into some of the boxes of EMA, here I've shown the energy consumption in production sectors, and it depends on the price of energy and the production. And what you can see is actually here, this drop in the energy consumption is due to very large oil price increases. And you can see that the change in the total energy demand is much lower than the change in production. That is, we have quite some considerable efficiency improvements over the time. And at this level of aggregation, efficiency improvements is at least partly due to structural changes, and over the period we have actually closed more or less all our energy-intensive productions in Denmark. In EMA, we operate with 22 production sectors, which are a subdivision of atom sectors. Typically, an atom sector is subdivided into an energy-intensive and a less energy-intensive subsector. Concerning modeling, what we try to model is the demand for energy services. That is, we model in energy-efficient units. We assume constant return to scale. We estimate an energy price elasticity that on average is -0.2, and prices are important both for the level of energy demand and for the substitution between different fuels. And finally, we estimate some trends in efficiencies. In forecast, these efficiencies are exogenous. Looking at the household energy consumption, households use energy for heating, for electricity, and for transport. And if we start by looking at heating, we see a considerable decrease in the 80s due to the oil price increases. After that, heating has been almost constant. It's not very clear, but the electricity consumption has increased slightly over the entire period, and the transport energy has increased quite substantially over the period. The three different uses are modeled separately. So if we start by looking at heating, in general, the model forecasts that the energy consumption follows the dwelling area, that is the heated area. We estimate a long-term price elasticity of -0.4, and we have annual efficiency improvements around 1% per year. Looking at electricity consumption, we distinguish between apartments, single-family houses, and second homes. And as you can see from this figure here, for single-family houses and apartments, the consumption per household has been almost constant over the period, while for second homes, we have a considerable increase in the electricity consumption and quite high level of consumption. In the modeling, the demand follows, it depends on the income and the price of electricity. And for both apartments and single-family houses, we estimate an income elasticity of 0.4, and the price elasticity is slightly higher in single-family houses than in apartments, which makes quite good sense. For second homes, we have not been able to estimate price elasticity, so it's 0 in the model. On the other hand, the income elasticity is 1. Looking at transport, the energy demand for transport has increased about 50% from 1980 to 2000, but it has actually decreased 15% over the last 5 years. And this is partly due to the introduction of small, cheap, energy-efficient cars. In the modeling, we distinguish between transport to and from work and transport for leisure purposes, and our behavior in these two transports are actually quite different. I won't go into details with that just now. Using the model for forecast, we need a number of inputs. First of all, we need a forecast of the economic development, and this we typically take from the Ministry of Finance using the atom model. We need inputs concerning the general energy price, and those we take from IEA. We need inputs for the electricity price. This we take either from Econometrics or from the Energy Agency. And then, as I said, efficiencies are exogenous in the model, and in the projections that I'll show you in a little while, we have assumed that potentials with a 4-year payback period are introduced over 10 years. this implies an annual efficiency improvement of 1.5%. Estimated on the past, the efficiency improvement is 0.3. So what we actually introduce here is new energy savings of 1.2% per year, which actually is a quite substantial effort on energy savings. Then I'm going to look at the electricity forecast. For the electricity forecast, we introduce new electricity consuming technologies. In this case, we have introduced 300,000 electrical vehicles in 2030 and 450,000 individual heat pumps. Looking at the forecast, looking first of all at the conventional uses, the blue and the green area, we see that this consumption is almost constant throughout the period. This is mainly due to the very large efficiency improvements that we have assumed in this forecast. Electrical vehicles add additional 3%. That's actually not very much. Individual heat pumps add an additional 8% in 2030, and that's actually a quite large amount. So in total, the electricity consumption increases 15% from 2010 to 2030, and that's actually not very much. It's less than 1% per year. We've had periods where the electricity consumption has increased much more than that. That was the electricity consumption on an annual scale. Now I go on to the electricity consumption on an hourly scale, and I made a little model forecasting the electricity consumption at the national level. This is important for the dimensioning of the production capacity, and it is important input to energy system models like Balmoral or Wilmer. The model is based on hourly data from about 4,500 representative customers categorized in a number of aggregated categories. This data is, as I said, collected by Econometrics and the Danish Energy Association. And for this model, I looked only at aggregated categories of customers and only on data for 2010. The idea is very simple. At the annual level, we have the forecast from EMA on different categories of customers. We know, or at least I will show in a little while, that the consumption profiles for different categories are very different, meaning that at the aggregated consumption profile will change if the weight of individual categories change. So that's what I'm actually trying to model. Looking just the one week in the winter, here I have shown the hourly consumption over the week, and we see that we have two daily peaks, and midday peak and an evening peak, and we see that consumption is high on work days and low in weekends. Now, how does individual categories contribute to these profiles? If you look at households, they mainly contribute with the evening peak and the demand consumption in the weekends. Agriculture has a small daily variation, and all days look more or less the same. Industry has a midday peak from 8 a.m. to 4 p.m., and it doesn't use very much in the weekends. Private service sector has a very long daytime peak, and it even uses some both Saturday and Sunday. And the public services have a very short daytime peak. It has very little consumption in the weekends. And what we can see is a small evening peak there, and that's actually public lighting. it was a surprise to me where it came from, but it's public lighting. So overall, production sector is mainly consumed during daytime on workdays, and households mainly consume in the evenings and in weekends. Now, that was just 1 week. Looking at the seasonal variations, you see here, this is just the average consumption, average profile for different months. So we have the general profile is the red one at the top. We have a very large consumption in January, and the low consumption is July. So we see that we have a very large consumption in winter and low consumption during the summer. And the other thing to notice is that the evening peak actually disappears in the summertime. Now, how does the different categories contribute to these variations? The main contributors to the seasonal variations are households and public services, where we have very large differences in the monthly curves. In agriculture, we have some variations. This is mainly due to horticultural sub-branch. Industry has almost the same profile all the year. The low one for July is due to the summer holidays in July. Private services has almost the same profile all months. So as a joke, comparing private and public services, you see in the private services, they work very long. They even work in the weekends, and they don't have any holidays. While in the public sector, we have very short working days. We don't do anything in the weekend, and we have very long holidays. Now, if we want to model this, we need to distinguish, of course, the different categories. We need to distinguish between hours of the day, months, types of day, and we need to allow the profile to differ for different months. Now, in the literature, there are 2 different models looking into this. The first one tries to describe the hourly variations using a number of trigonometric functions with different periodic frequencies. The advantage of this model is that it has very few parameters, but they are very difficult to interpret. The other model, type of model, use a number of 0-1 variables representing hours of the day, months, types of day, etc. This gives a considerable amount of parameters to estimate, but these parameters are easy to interpret. So I have chosen the last one. Mathematically, it looks like this. It may be a bit complicated to look at, but if you look just at 1 hour, the consumption is simply the product of 3 coefficients. One coefficient describing the profile for the daily profile for the given month. Another coefficient describing the relative position of the monthly profile. And the last coefficient giving the absolute value for the type of day. Now, as I said, there are quite a number of parameters in that, so we can try and test whether some of the parameters could be identical. If you look at this figure for the week, I showed that for agriculture, it looks like that all days are the same, so we test where work days and non-work days have the same coefficients. For industry, I showed the Fridays were short, so we test whether Fridays and other work days are the same. And for private services, we had this peak in Saturday and Sunday, and we test whether those peaks are the same. We use what is called a log likelihood ratio test, and what we actually see is that the test values are very much higher than the critical values, so we actually reject all these hypotheses that the coefficients should be the same. Another hypothesis is that the profiles, but not necessarily the level, is the same for all the months. That would really reduce the number of parameters to estimate. Again, we do a log likelihood ratio test, and again, the test value is much larger than the critical value for all the categories except for the industry. So actually for industry, we accept that the profiles are the same, but not necessarily the level. So for the final model, for households, agriculture, public service sector, we distinguish between workdays and non-workdays, and the daily profile differ between the months. For industry, we distinguish between Monday to Thursday, Friday, and non-work days, and daily profile is the same for all the months. And for private service, work days, Saturdays, and other non-work days, and the daily profile differs between months. And that's what we have estimated. And if you look here at the upper part of the table to start with, you can see that the model explains around 95% of the variation in the hourly consumption. So we are actually quite systematic, doing the same thing, the same day, the same hour every day. Yes, sorry. The other thing you can see is that the Watson statistics are very low. That is, we have a very large positive autocorrelation, implying that some days are different. It's cloudier, it's more colder than normal for the year. So if we have a positive error 1 hour, we'll probably also have a positive error the next hour. This is, of course, very important if you're going to forecast the next day or two. What we are looking at is the profiles 10 to 20 years ahead. So it's not very important for this model or for this analysis. If you take it into account, the model is able to explain around 99% of variations. So we really do the same thing every day. Now, using the model for forecasting, we assume that the profile for the individual categories of customers is constant. We assume that the annual electricity demand by category, we use the forecast from Adam to scale up and down the different categories. Here I've just shown that from the latest electricity forecast I showed you before, that from 2010 to 2030, the total electricity consumption increased 4%. The household has almost the same consumption. We have a slight decrease in the agricultural consumption. We have a large decrease in the public service sector's consumption and an increase in the private service sector's consumption. Looking only at those and looking at the profile in July and in January, what we actually see here is that the profile is almost the same. It's not really changing, even though we have a very large increase in the share of the private service sector. Now, if you introduce the new electricity consuming technologies, we had the 300,000 electric vehicles and 450,000 individual heat pumps. We assume some fairly simple profiles. We assume that electrical vehicles are charged mainly during the night, and that all days are the same. And for the heat pumps, we assume a normal heating profile in Denmark. If we now just look at the profiles for 2030, you can see that the electrical vehicles add a little to the consumption during the night. if you look at the heat pumps, they mainly contribute to the consumption during the winter, where the consumption is very high already. So the implication is that either we increase the conventional production capacity, or we get some of the heat pumps or some other consumption to be flexible and move the consumption until the night time. As a footnote, just at the moment, households have absolutely no incentive to become flexible. That was at the national level. I think I need something to drink, sorry. As I said, I've also made a small model looking at the hourly electricity consumption in local areas. The data we use is hourly consumption from transformer stations, each covering a local area. At present, I have only looked at Denmark West, DK West. We use the profiles. We have the profiles for the categories of customers, the same data as I used in the other model, just looking at DK West only. And then we use data for 3 years, 2009 to 2011. That is, we have around 26,000 hourly observations. And what do we know? We know that the consumption profile for the different categories are different, those down here. And we also know that the weight of customers differ in the different local areas. So what do? We use the profiles down here to find the weight of different categories in the individual local areas. Now, when we forecast, we assume that the profiles and the weights are constant. Then we use the national forecast to forecast the profiles in the local areas. We have a total of 62 transformer stations, and here I've just shown 4 quite distinct, quite different profiles. The first one up here is Hasle, that's the center of Aarhus. What we see is that we have a very long daytime peak and a little evening peak, mainly indicating that we have a large service sector there. We have a mixed area it's called Hatting, where we have a very large share of industry. You can see you have a low consumption in July. You have an agriculture area, Nipstrup, where they have a slightly low daytime peak and a large evening peak. And we have a large consumption in July. That is, we have very little industry there. And then we have a sparsely populated area, Storstrup, where we have a very large daytime peak, somewhat some evening peak, but not that high, and especially not shown. The daytime peak is very large on non-work days. Now, what we try to do is we try to weight the figures on the last slide to fit the curves on this slide. And it actually works for most of the areas, but not all. If you look at Aalborg East here, it's quite evident that this profile we cannot explain by the profiles for the individual categories. I'll come back to that. Now, the model is actually very simple. We use the profile at the aggregate level, and we weight these to give the consumption profile in the local area. So the share of an individual category in an individual area is just a coefficient times the same category in the aggregated area. So if this coefficient is larger than 1, then category J has a larger weight in the local area than in the aggregated area. That's a very simple equation. The estimation problem is that we have 62 equations, and these need to be estimated simultaneously due to some constraints and come back to. And we actually use 3 years of observation, that's 26,000 observations. So suddenly it becomes somewhat of an estimation problem. The adding up restrictions, looking at an individual area, local area, we would like that it shares for the individual categories add to 1. Looking over the different areas, we would like that for each category of consumption, the consumption in each local area adds to the total in the total area. Yeah. And then we'll need that all the coefficients are non-negative. A negative coefficient would imply that we have a negative contribution from the consumption. This is not feasible. To just show a simple case, here I've aggregated to only 4 aggregate areas. Towns, mixed areas, agriculture, sparsely populated area, and that's a simple estimation problem. What we see is that private and service sectors have a quite large weight in towns. In mixed areas, we have a large weight of industry. In agricultural areas, we have a large weight of industry, but not a very large weight of agriculture. The agriculture is actually situated in the sparsely populated area. One thing to notice is that the model at this level of application actually fits quite well. Now coming to the final model, we have estimated all the local areas. We have some problems. Each area consumes around 1 to 5% of the total electricity consumption in DK West. And we have some of the profiles that are not very easy to explain. So for some of the areas, some of the small areas, we have had to aggregate it with neighboring countries. Doesn't really matter in the planning. We have a last area with 5 transformer stations, and there we actually have Aalborg East, and this might give a problem later. So in total, the 62 local areas are aggregated into 52 local areas. We have some non-negative, some of the non-negativity constraints are binding. So all the equations need to be estimated simultaneously with the adding up restrictions imposed. If you look at the R-square variance, they are a little lower than for the aggregated areas, quite natural. The relative variation in local areas are larger than in aggregated areas. The weights are very different in the different areas. In general, I'll say the coefficients appear quite reasonable. Now, using the model for forecast, we assume that the weights are constant, we assume that the profile is constant, and then we assume that the level of consumption for each of these change the same in all the areas. Here I've just shown the same forecast as I showed before, so I won't go into that. Looking only at conventional consumption, that is excluding electric vehicles and individual heat pumps, what we see is we have a very large difference in the average expected change in the average consumption. In one area, the average consumption increases 8%. In another area, it decreases 4%. In general, we have increases in town areas with a large service sector. That was where the aggregated forecast shows us an increase. And we have a decrease in sparsely populated area with a large agricultural area. Another thing to notice is that the profile actually changes. For some of the areas, approximately half of the areas, the maximum consumption increases more than the minimum consumption, and the other half of the areas, the minimum consumption increases more than the maximum consumption. So we'll have a shift in the profile in different areas. haven't said much about it, but the method that is used at present, it assumes, it looks only at the maximum consumption, and it assumes that this consumption increases the same in all the local areas, and that is 3.8%. Now, including electric vehicles and heat pumps, we have used just the same profiles as we did in the previous forecast, but we have distributed the consumption on the local into the local areas as the electricity consumption is today, as an indicator for where the private households are. Okay? Doing that, we have quite large difference in the effects on the different local areas. In this area, Hostrup, we have a very large increase due to the individual heat pumps. In Estrup, we have nearly no effect. Quite interesting observation is that in DK West, the present methodology would say that the maximum consumption should increase 14% in all local areas. We can only find one area, and that's Ferslev, where we will have an increase that's that large. All the other areas have a lower increase in the maximum consumption. The reason is, of course, that the weight of household consumption in DK West is very much lower than in aggregated for Denmark. So in summary, the new model is what I call a first step towards a differentiated local forecast. The model takes into account that the composition of categories of customers differ between local areas, that consumption per category contributes different to the aggregated consumption profile, and that the level of consumption per category is expected to change differently. What it doesn't take into account is that the profile per category may differ in local areas. For instance, due to different composition of industry and agriculture. If you look at households, it's quite safe to assume that the profile is the same in all the local areas, but due to the composition within industry, these are situated, the profiles may be very different. Another thing it doesn't take into account is that over time the profiles may change, for instance, due to increased demand flexibility. And finally, the weight per category may change, for instance, due to the development of a new dwelling area or a new factory or closing of a factory. So that we don't take into account at the moment. So at the moment, we have looked only at DK West. We expect to continue with looking at DK East. And as new information becomes available, we'll probably try to consume with some of those issues here. Thank you. Should be time for a few questions, or what?
Exactly.
One or two.
Opportunity for a few questions. You want to come up with some questions?
No?
Yes.
You had some bits on the number of electric vehicles and heat pumps.
I had what?
300,000
Yes.
electric vehicles and 450,000
Yes.
individual heat pumps.
Yes.
First of all, these individual heat pumps, do they include, I expect they don't include district heating heat pumps.
No, they don't.
So you've not taken that into account in your model. And then the question is, where did you get these numbers from?
From Energinet DK. That's their assumptions to make the electricity. The forecast that showed is the latest electricity forecast by Energinet DK. So that's their assumptions, their forecast. So I think it's quite a large number of individual heat pumps, but that's their decision. So, Okay. Thank you for a very interesting presentation, Frits. Thank you.
Then I have two questions for you.
Okay.
And the first one is, we just have implemented a new data hub,
Yes.
where we will get plenty of data measured for all customers on an hourly basis, actually.
Yes.
And this is really a radical change in data in Denmark.
Yeah.
Will it radically change your possibilities for estimation, or how will it influence your work?
There are two answers to that. The first one is that it opens for a huge amount of analysis. And I mean, we are very fortunate in Denmark because we actually have the data hub. We have hourly metering all over Europe. But if we are able to get access to those data, we could make a huge amount of new analysis looking into income distribution effects, whatever, really many things. If I just looked at the last model here, then it would be more or less obsolete saying that if we have the weight of the individual categories in individual local areas, why should I estimate it? So it changes, of course, the scene, but it requires that we get access to the data. And I hope we'll get that once. So, but there are, yeah.
Okay. My second question. We saw from your presentation that public consumption of electricity actually decreases quite much within the next 10 years or something.
Yes.
Is that because of a wishful thinking production forecast made by the Ministry of Finance, or what is the reason for that?
Well, it's a combination. It's a combination of a low forecast on the production from those sectors, but also that we have the very large efficiency improvements that we assume. So it's a combination of the two.
Is it a realistic forecast?
Of course it is. We are just at the moment we are updating the forecast. So if you come back in a month or two, I'll probably have a completely different view on what is the probable forecast. Okay, sorry. But of course I can't say anything else. Okay. Yes.
So I wondered if we already saw in the data, last year in 2012 we had a huge increase in photovoltaics on households. If you are already seeing that in the data and how you can...
I haven't seen that. I haven't seen that at the moment. I have 2011 data. That's the latest figures we have. I don't have any data for 12.
How would that change your forecasts?
What I'm trying to forecast, is actually the demand development. What you are saying is that what's important for the capacity is the net demand. And I have to think about that. I actually don't really know how to cope with that one, but we will have that problem maybe with solar panels. So, yeah.
Right now we have the one-size-fits-all approach for the whole of Denmark regarding network extensions and peak demand forecasting. How much money could we save if it's individualized for the single areas and heat pump electric vehicle, changing from the old approach to the new one? Do you have any idea what engineers say how much money they can save if they apply this data to future network extensions?
No, I don't know anything about that. I know that the plan is that Energinet DK will use the model in their next net planning. But whether they are going to earn money on it, I don't know. Of course, I hope they will, but it's not my problem. So, okay.
I'm very thrilled to see a study of the geography of electricity demand presented by
an economics professor. And I think there may be so many further interesting aspects here that we haven't explored yet.
Yes.
Can you think of, and maybe we could make a map. Well, we can do it simply. But
I mean,
apart from the grid issue, do you see any other lessons or uses of this kind of information, like regional development?
You might use it for that. I'm actually doing it the other way around, if I'm not misunderstanding. I'm taking the national forecast and then I use the weight and this in local areas, and this of course gives that you'll have a very slow increase in the agricultural or sparsely populated area, at least when you look at the electricity consumption. If you say this reflects the economic distribution also, which it to some extent will do, you can say something about regional differences in the economic growth. But I mean, there are models for regional economic forecasts. They exist, so I propose you use that instead. I mean, it exists. The link to the energy is okay. I mean, that you could easily. I mean, the local model is actually based on local data, defined by transformer stations. So.
Another question? Okay. Which I'm wondering, I would expect that this would be a great tool to identify where energy savings could provide the best benefits and where it's also possible that savings and demand flexibility could matter because you have large fractions of households, etc. Is that correct, or what do you think?
I'm not sure I understood your question.
If you could use this tool to identify where...
This tool, what is this tool?
Your tool with your
Econometrics in
shares, yes.
The last model?
Yeah.
Okay.
Can you find those areas where demand flexibility and savings matters the most, where they have the largest benefits?
What you... Not directly on this one, but if you combine it with the grid planning, you can see that this model will say that you will have a very large increase in one area. If that's a problem, you'll benefit from becoming flexible in this area. But I mean, I only do the forecast at the local. Then what they do in the grid planning, that's in a DK, that's not my not my expertise. I'm just analyzing the data. Okay.
Thank you. Thank you very much for your presentation, Frits.
Thank you.
I've been thinking a little bit about the productivity issue of public service, including universities, and either you produce more papers on the same time, or you have to work by night, not switching on the lights. I think then we'd end up in the results Frits shows. Apart from that, thanks a lot. Pleasure hearing your talk, and we're looking forward also what Erik said about the data hub.
Yes.
And exploiting that further with you as a leading professor in this area. So that's really good, cool, and thanks a lot. And there will be a reception afterwards.
Yep.
Now, in fact.
Thank you.
So take the reception first, and then go to Untitled Chapter if you have to. Thanks a lot.
Thank you.